Hey, ladies and gents, welcome back. Today, I don't know what time you're watching this, it's night for me. We are going to be creating entire polar graphs rather than just plotting points or talking about the equations. We're going to put it all together and create an entire graph. Now, personally, I think polar graphs look a lot cooler than the algebraic graphs you are used to, but I guess that is up to you if you agree with me. So you will notice, or you have already noticed, that I have linked the notes that we're going to be completing right there on Canvas. I would highly suggest, if you have access to a printer, to print these out. Since we are going to be creating graphs, you're going to want to be able to plot points and connect them. But if you do not have a printer at home, if you save this doc as a PDF and use the Kami extension, then you can go ahead and write right onto these notes. That will help tremendously. If you need help setting Kami up or learning how to use it, let me know and I would be happy to help you. I would also suggest you have your calculator. I'm going to teach you something on there, but we're also going to use it to plug values into our polar equations. And if you do not have a TI at home, technically any calculator will do this for you, your computer included. But in your computer, if you paid attention to the module about having calculator access at home, if you open up your apps in your your computer, and scroll down to the bottom, you should hopefully see one that looks exactly like this one. TI 84 plus CE, the school district pushed that out to all of the school Chromebooks. If you don't see that, need help finding it, again, please let me know. So without further ado, I'm going to flip my computer around. And here we go. Okay. So we've talked before about why polar equations, why polar points. Well, we know polar points are the more it's how we describe the location of any place or position in real life, a distance and a direction, not a horizontal and vertical distance. But we'll also see that some polar equations, and I said this in the last set of notes, sometimes and many times really, polar equations are the easier way to represent an equation versus representing it in the rectangular form. So take a look at this rectangular equation. Many of you would recognize that this is the equation of a circle. Now, if I wanted to graph this circle in my calculator, if I didn't know that app that I showed you once in class existed, I would have to get y by itself. Well, getting y by itself for a circle is really, really difficult. First, I have to write this equation in the form where I can recognize the center and the radius of the circle. To do that, I would have to go through the process of completing the square, which I'm going to do really quickly. I know I've run through it briefly in class before, but for those of you like, I don't remember this, it just goes to show this is really difficult to put in your calculator in the form y equals. To complete the square, I need to make these y's a perfect square trinomial. So to do that, I am going to have to make this factorable. So I'm going to divide my coefficient of my y term by 2 and square it. So I get 4. Whatever I do to one side of an equation, I do to the other. So I add 4 to the other. I now see that I can factor this trinomial with all the y's into two binomials, y minus 2 and y minus 2, or y minus 2 squared. There we go. We have a circle. And just for reference, this circle has a center at, there is nothing added onto that x, so 0. And for the y, we have a y value of 2. And I have a radius, remember this is r squared, so I have a radius of 2. Y still not by itself. So again, if I want to put this in a calculator, got to get y by itself. Well, to do that, I would have to subtract x squared to the other side. 4 minus x squared. Square root both sides to get rid of that squared. So I have y minus 2 equals plus or minus. If we didn't have that plus or minus, that would not give us a circle. And no, square rooting 4 minus x squared does not give you 2 minus x. Multiple terms, things separated by plus or minuses, do not square root that easy. I then have to add 2 to the other side. And to put this circle into my calculator, I would have to type in all of this. Whoa, that was a lot of work. And technically, we're not done, because how the heck do you type a plus or minus into your calculator? You can't. So to actually type in this equation of the circle, I'd have to type in y1, 2 plus the square root, and then in y2, 2 minus the square root, hit graph, and I would finally have my circle. Way too much work. a circle is way better represented as a polar equation. So we're going to do some converting. Keeping in mind those 4 equations that we had for converting coordinates and equations, I'm going to need 2 of them here. So I'm just copying those 2 down. And this was a different format for y divided by r. So I'm going to leave that there because that'll be helpful here shortly. So x squared plus y squared, same as r squared. Really easy to turn that into polar form. Polar, remember, we want all r's and thetas, not x's and y's. So we have r squared minus 4y equals 0. Now, yes, for that y, I could plug in r sine theta, would work exactly the same way. I'm going to do a slight different variation. I'm going to add 4y to the other side. I'm then going to divide by r because I'm trying to, only because I know where we're going with this. I'm just going about it a slightly different way. I know if I have y over r, I can put in sine. So to get that, I'm going to divide both sides by r, which gives me r equals 4 times y over r. Now I can make that substitution r equals 4 times sine of theta. And again, I recognize that I did this in a way that most of you probably would not. Again, I knew where we were going, so I might as well show you a different way. This is the polar equation for the exact same circle that is represented here that we would have to do all this work to get in the calculator. This, really easy to graph, and in a little bit I'll show you how easy it actually is to put into your calculator. So, how do we create this polar graph? And no, I'm not going straight to the calculator. Well, if you think about how you first created any sort of graph back in your, probably middle school days, you created a table. So that's exactly what we're going to do. We are going to create a table for this same circle, r equals 4 sine theta. We're going to pick theta values as our input. We're going to plug them in. We're going to come up with r values. We're going to plot a point and hope that we get this circle that we're expecting. So then the question is, what points do we plug in? Well, this is very much like the unit circle. Technically, this first circle, this r equals 1 right here, that little circle in the middle is the unit circle. And around this polar graph, we have all of these special unit circle angles marked. So that is exactly how we are going to go about creating our polar graph. We are going to plug in all of our special unit circle angles. Now you may be thinking, but that's so many. Well, yeah, but we're going to use our calculator help, so you'll be fine. So once you write these down once, you're going to need them pretty much with every polar graph you create. So you'll have them once and then you're done. Now, most of you probably have them memorized anyway, which is awesome. I would keep working on memorizing that unit circle, especially for any of you who are going to be going on to calculus at some point in time. So I'm into the third quadrant now. I know I'm going to run out of room on here, so I'm going to create another column here shortly. Here we go. Starting with 3 pi over 2 and into our fourth quadrant. 5 pi over 3, 7 pi over 4, 11 pi over 6, and I don't need to worry about 2 pi because that is coterminal with 0, so it's going to give me the exact same point. Okay. Now, I very, very much expect that you could plug in something like 0, pi over 6, pi over 4, and find the sine of pi over 4. However, think about the sine of pi over 4, root 2 over 2. I'm going to take root 2 over 2. I'm going to multiply it by 4. I simplify, I get 2 roots 2. If I ask you where 2 roots of 2 is as an r value on this graph, most of you are going to look at me like a deer in headlights because we don't graph naturally with roots. Decimals are more natural. So with that said, I'm going to let you use your calculator to plug things in. So first, make sure you are in radian mode. Good thing we're checking because I am not. And then we are going to plug things in. 4 times the sine of 0. 0. Easy peasy. 4 times the sine, I would type things in as fractions, helps avoid mistakes, of pi over 6, 2. Again, really easy. 4 sine pi over 4. Okay, there we go. Decimal. 2.828. So Mrs. P, how many decimals do you want? Well, think about what we are doing with these values. We are graphing. Would you see on a graph 2.8 versus 2.82 or 2.828? not on a graph this size. Because this graph is so small, it is totally okay that you round to the tenths place, because visually we are not going to be able to see the difference between tenths, hundredths, thousandths, or whatever place. Don't round it to the nearest integer, but to the tenths place, totally appropriate. So with that said, I feel completely confident that you all can plug in some points and give me some coordinates. So feel free to pause the video at this point and go ahead and plug in the rest of these values, and then unpause it and you can verify them with mine. So for all of you all who are back, you are going to watch me copy down the coordinates, or the R values, excuse me, that remain for these points. And then we are going to go through and we are going to plot them. Negative 3.5. I think my purple pen is finally starting to run out of ink a little bit. See if it makes it through these notes. Okay, verify your points. Mine should be good to go. Now keep in mind, polar points are plotted actually as R theta. So our table is technically a little bit backwards, but personally, I find it easier to identify theta first and then go count out how many units away from the origin you need to be. Now, pro for us, these are already in unit circle order. So if I start at 0, I know that each next important angle that's marked on here is going to correspond to one of these. So everything's in order if we just work in order starting from 0. So 0, 0. Well, angle of 0 is here, but 0 units away from the origin would put me right there. Note, anytime your R value is 0, you're going to be at the origin. So pi over 6, we are going to be 2 out. Pi over 4, we are going to be 2.8 out. And again, just guesstimating, you can see why 2.8 versus 2.828, you wouldn't know the difference. Pi over 3, we are 3.5 out. Pi over 2, 2, 3, 4. And I'm going to keep going. 3.5. 2.8. 5 pi over 6 is 2. And hey, look at that. At pi, we have an R value of 0 again. So that's going to put me right back here. Moving into the third and fourth quadrant. Ooh, look at this. We have negative R values. Remember that a negative R value means that we are going to slide back through the origin. So first thing I'm going to do is identify that theta value, 7 pi over 6. If it was positive 2, we'd be right here. But because it is negative 2, we are actually going to slide back through the origin 2 spots. And we'll actually notice that that is the exact same point that we had right here with pi over 6, 2. Continuing, 5 pi over 4. 2.8, but it's negative, so I'm going to slide back through 2.8. If I keep going, I'll actually find that all these third, fourth quadrant angles will recreate these points that we already have plotted, so I'm not going to walk through them. Now, we already know we are expecting a circle, so maybe you can see we have a circle right here. But what if you can't see your shape? What if you feel like you're missing points? What if you know what shape to expect, but you're not sure how to connect the dots? Well, think about what you would do with any other graph you're creating. You would plug in more points. Now you may be thinking, well, what other points do we have to plug in? Well, a unit circle has special angles, but it has an infinite number of angles around it. So pick more angles. This is 30 degrees. So if I had picked one before that, I'd be at 15 degrees. Now I happen to know that 15 degrees is pi over 12. You can always convert 15 degrees, or you can change your calculator to degree mode and type in 15 degrees. I'm also going to do 75 degrees, which is 5 pi over 12. I'm going to do 105 degrees, which is 7 pi over 12. And I am going to do, what would this be? 165 degrees, which is 11 pi over 12. I'm going to try and fill in the blanks of this circle. So going to my calculator, for sine of 11 pi over, or we'll start with, well, I guess I'm going to start with 11 pi over 12. I don't know why I did that. 11 pi over 12, we're going to go backwards, is about 1.0. So we're going backwards. We'll go to 7 pi over 12, which is about 3.9. 5 pi over 12, which is about 3.9 again. And pi over 12, which is about 1. So plotting those points, pi over 12, 1 out. 5 pi over 12, 1, 2, 3.9 out. 7 pi over 12, 1, 2, 3.9 out. And 11 pi over 12, 1 out. That gives me a little bit better definition in my circle. And again, you are welcome to pick and encouraged to pick more points around the circle, degrees or radians, to help you verify the shape of your graph. Now, going back to our notes, just for comparison purposes, we had said our circle with rectangular coordinates would have a center at 0, 2. So imagining that this was an XY coordinate grid, 0 over, 2 up. Yep, that would make sense for the center. And we had said I should have a radius of 2. So looking at this guy, 1, 2 up, 2 down. Yep, this looks like the right circle. Kind of cool, right? You're like, well, it's just a circle. Like I said before, there's actually some really cool looking polar graphs. Now, is it possible for me to show you every single polar graph in the world? Heck no, definitely not possible. But it's also not possible for me to show you all the different Cartesian coordinate sorry, I have a crying baby in the back. All the different algebraic graphs you could ever see. But there are some that you're going to become more familiar with. Now, if you think about all of the graphs that you have ever seen algebraically, you learn them over years, not minutes or hours, but years. So we don't have years to learn all the different polar graphs you could expect, but page 899 in your book has them, and you'll notice we've got some pretty cool shapes in here. Now, if you, for whatever reason, did not bring your book home, page 899 is actually linked under modules under naming polar graphs. So you can absolutely look there. So here's what we're going to do. We're going to create one more graph together. I'm going to have 2 more optional. I'll have another video showing me working through creating those graphs, or you can just verify it with my PDF. But not only are we going to create those graphs, we're then going to talk about what type of symmetry do they have, because we actually talk about symmetry slightly differently in the polar world than we do when we're graphing on XY coordinate grid. We're going to talk about naming them. If you think about graphs that you know names of, parabolas, I guess absolute value doesn't really have a name, cubic functions, the shape doesn't have a name, but we can identify them. And there's also key features of those graphs that we know about, and we're going to talk about identifying some key features of these polar graphs. So we're going to do some practice, and then again, I will have some optional practice linked up that you can watch or just verify. So I'm going to go out of order, and let's go with, let's say, number 3 from your notes. So actually, you know what, before that, let's talk about symmetry. Before we talk about number 3, let's talk about symmetry. So I actually went ahead and I filled this in already for you. In the polar world, we actually, technically speaking, don't have a y-axis, x-axis, or origin. In the polar world, because we are not graphing x and y coordinates, we are graphing r and theta coordinates, we rename those. And so from this point forward, I want you to practice using those names. So what we used to know as the y-axis is actually referred to as the line theta equals pi over 2. Makes sense because here's pi over 2 right here. Now, I put in that means if we have a point over here, we have a point over here. Actually also put in those what those coordinates would be. And I think I mentioned already, there's going to be this optional set of notes for you to watch. For those of you who do watch that, we'll talk more about this point right here. But I know y'all know how to reflect using symmetry, so that is key. Symmetry with respect to the polar axis. It's no longer the x-axis since we don't have x coordinates. It's called the polar axis. So if I have a point up here, I have a point down here. And we no longer have an origin. We have a pole. I like to think of it as the North Pole is the top of the earth. In my head, that's where Santa lives. So that is why this is called, the center is called the pole. And that is like sliding back that negative r value. If I have a point up here in the first quadrant, I have a point down here in the third. If I had a point up here in the second quadrant in symmetry with respect to the pole, I would have a point down here. So we'll come back to that because again, once we create some graphs, we are going to identify the type of symmetry I guess referring back to the circle that we just created, we'll notice that I know we all want to say we have a y-axis symmetry, but we aren't going to call that y-axis symmetry. We would say that this circle has symmetry with respect to the line theta equals pi over 2. Now, had I known about that symmetry prior to graphing, that would allow me to pick points just from one side of theta equals pi over 2, plug them in, and then flip it over. But unless you were going to watch these optional notes, you won't know how to do these tests for symmetry. So that is why we have to plug in all of the points. If you want to avoid plugging in all of the points, then watch these optional notes that you're going to hear more about later. So now we are going to jump to number 4. Where did I just put that piece of paper? Here we go. Now we are going to jump to actually number 3, I think I said. Number 3. So we'll notice this does not look exactly the same, my equation, as the same form as my circle. So we're going to use page 899 to help us predict what type of shape we should get. That'll help with our graphing tremendously. So how do we do that? Well, on page 899, trying to get my book to show it, we have a couple different families of polar graphs. We have these things called limacons, and we'll notice we have 4 different limacons: inner loop, cardioid, dimpled, or convex. All of those equations come in the form of A plus or minus B cosine or sine of theta. So big kicker here is I have a plus or a minus sign. I don't have that in number 3, so I should not be in the limacon family when I'm done. Moving on, rose curve. Well, if I'm a rose curve, I should have a coefficient of cosine or sine. I have that. And I should have a coefficient of theta. I have that. Looks like we should be in the rose curve family. Knowing this in advance of actually creating the graph will help me, connect the dots and help me ensure that I've plotted points correctly. Now, I'm going to come back to this, but just looking. Circles, I know that this is not in the circle family because notice this coefficient of theta that we have, the circle family does not have that. And lemniscates contain r squareds. I definitely don't have any r squareds. So we know we are in the rose curve family. Now we have different types of rose curves. We have rose curves with even number of petals. We have rose curves with odd number of petals. We can actually do one better than just knowing we have a rose curve. Based on this 4, which we know represents our A value, so I'm going to put a little A in front of it. And based on this 2, which is our N, we should be able to predict more about our rose curve. So looking up here, we know we have N petals if N is odd. Well, our N is 2. So N is not odd, it's even. So we have 2 times N petals if N is even. N is even, so I know that my petals are 2 times N, or 2 times 2 in our case, which is 4. We have 4 petals on our rose curve when we're done, or we should. So what about A? What does A represent? Well, looking at this graph, I can see that A is measured from the origin to the tip of a petal, or from an axis to the tip of the petal, however you want to look at it. A represents the length of a petal. So we have length of a petal, in our case, is 4. Now, again, I'm not expecting you to memorize this, page 899 in your book, but it'll help tremendously with playing connect the dots and ensuring that we have created the correct graph. So, how do we create the graph? Here it comes. We are going to plug in all of those points. So if you want to go back to the one that we created, the circle we created previously, to help you come up with all of those unit circle angles, please do that. Or you can watch me, well, you're going to watch me either way, write them all down here. There we go. I got first and second quadrant done. On to the third quadrant. Gonna run out of room again. I'm gonna see if I can avoid having to do non-special angles. Knowing and predicting what the graph type, shape, and some special things about it, like number of petals and length, could also help you avoid having to plug in those pi over 12s and things like that. Okay, and again, I'll let you go to I'm going to let you go to your calculator. I'm going to clear that out. And we have 4 cosine of 2 theta. So 2 times 0, we get 4. Going to change that theta value to a fraction now. Pi over 6. We get 2. If you want to pause at any point in time, so you are not watching me type all of these in, you want to give it a try on your own, you are absolutely welcome to do that. So feel free to pause at this point. And if you are unpaused or did not pause, I do not have these pre-written down anywhere, so I am typing them into my calculator right along with you, doing exactly the same work that you all are. Whoops, don't know what I did there. This should have been my 3 pi over 4. Now, if you get anything weird like this in your calculator, I don't know why it can't handle it, but that's really 0. It's teeny tiny scientific notation. Should be very familiar with scientific notation. Now, let's see. I don't want to have to get rid of my fraction to type in pi, so I'm going to do pi over 1, 7 pi over 6, 5 pi over 4. Again, that's a 0. Why it does that, I do not know. 4 pi over 3, 3 pi over 2. Notice we're getting a lot of the same points, so that actually is going to tell us something here. We'll talk about that more here shortly. Almost done. Again, that would be a 0 and 11 pi over 6, 2. Perfect. Okay, all the way around the unit circle. We named it, identified the shape. We know key points about it, so let's plot the points. So angle of 0, 1, 2, 3, 4 out. Now it is really promising in our table that the largest number we see is 4, knowing that we should have a petal length of 4. Nothing should go past that. Pi over 6 is 2. Pi over 4, 0. Remember, anything with an R value of 0 is at the pole, not the origin. Notice these negative R values. Be careful. Pi over 3. Now if it was 2, it would be here, but negative 2, I'm going to go right back through the pole. There's my negative 2. Pi over 2, I'm going to slide down pi over 2 through the pole and out 1, 2, 3, 4. 2 pi over 3, I'm going to slide back through the pole, 1, 2. R value of 0, I'm right back here. 5 pi over 6, 2, and it's positive, so I can stay right here at 5 pi over 6, would be right here. 5 pi over 6 would put me at 1, 2. Pi would put me at 1, 2, 3, 4. 7 pi over 6 also happens to be at 2. 5 pi over 4, R value of 0, right back at the pole. 4 pi over 3, negative 2. So even though this is 4 pi over 3 through the pole, 1, 2. 3 pi over 2 through the pole, 1, 2, 3, 4. 5 pi over 3 through the pole, 1, 2. 7 pi over 4, R value of 0, right back there at the pole. And 11 pi over 6, 2. Now, while that looks like a big mess of points, again, if you plug in those 15-degree increments, those pi over 12s, that would be my next suggestion. Absolutely can do that. But if you also think about the fact that we need 4 petals, each with a length of 4, and if you take a look at your book, we do have in your book one rose curve that has 4 petals. This particular rose curve happens to be turned a little bit differently than the one in your book. And think about that. That's okay. Not all absolute value graphs are the same. Not all parabolas are the same. So not all rose curves are going to be the same. But knowing this is what we need to expect, that may help many of you see that we actually have enough information to create our rose curve right there. How pretty is that? It'd be really fun if we could decorate these right now, but doing that virtually is a little bit tougher. Again, if you're like, I wouldn't have seen that's how to play connect the dots, your best bet then is to pick some more points, plug them in until you can be sure that you're playing connect the dots correctly. Now, symmetry. You'll notice this rose curve has tons of symmetry. We have symmetry with respect to the line. I'm going to identify my symmetry here. Symmetry with respect to the line theta equals pi over 2. Had I known that, then I could have plotted just plugged in points from over here and flipped them over. This graph also has symmetry with respect to the polar axis. So if I had known that, then I could have just plugged in points from up here instead and flipped them over. This graph also has symmetry with respect to that pole. That should have been identified from all the sliding we did. This particular graph happens to have all three types of polar symmetry. Now, had we known that prior to plugging in all of these points, we would have had to plug in far fewer because, again, we could have plugged in and reflected. Now, could we have known that just based on the information we have this far? No. But for those of you who are going to opt to watch the optional videos, optional notes later on next week, then yeah, you could figure out how to predict symmetry prior to actually creating the graph. But for now, to create the graph, plugging in all of those unit circle angles, adding some special angles if needed. Prior to doing that, though, using page 899 to predict the shape and key aspects of that shape, that will help you ensure you've plotted correctly, and it will help you play connect the dots. And after you have the graph at this point, you should be able to identify what types of symmetry your graph indeed does reflect. So with that said, I want you to try 1, 2, and 4 from the notes. Try them on yourself, by yourself. If you want to just verify with my key, my PDF that I have available, feel free to do that. If you want to watch me walk through those remaining three graphs, I will post a video of me walking through those 3 as well. But otherwise, after that practice, there's additional practice available in your book. And the last thing I want to show you, your calculator. Almost forgot until I looked over my shoulder and saw my notes. Your calculator can graph these as well. You know what? I am actually going to switch to the calculator built into the computer because that's going to show up a whole lot nicer for you. So here we go. We're going to stick with our rose curve right here. I'm going to get rid of this extra picture of me. We're going to stick with our rose curve. How the heck do I put this into my graphing calculator? Because it can happen. First and foremost, make sure you are in radian mode. We already are. So that's good. Let's see if I can make this bigger, not too much bigger. Second, you will notice underneath mode, we have function, parametric equations, polar equations. We need to change this from functions. You'll notice polar equations, polar graphs are not functions. They do not pass the vertical line test. We're going to switch it to polar. In doing that, once you hit your y equals, you'll notice you no longer have a y equals. You have an r equals, which makes creating these graphs in your calculator so easy. So going with that graph we just created, 4 cosine 2 theta. Now watch this. This is what makes me really happy. I'm going to hit that variable button for x, and I get my theta. Yay! I've typed my equation in. I know I should be getting this 4-petaled rose curve with length of 4, but because this is still trig-based, it will really help you before you hit graph to zoom 7, zoom trig, and look at that. Isn't that beautiful? And take a look at that. Also looks like the graph that we made by hand. Mrs. P, can I cheat and just use my calculator? No, I want you to practice creating these by hand, but also aside from being able to name it and identify key features of a graph, you can also use your calculator to help you verify that you've indeed created the correct graph. Now, if you scroll down to the bottom of your notes, you will notice that I have all of those steps for putting this into your graphing calculator available there, so please check it out. If you got any questions, let me know, and I will talk to y'all later.